Space doesn't play by the rules, at least not the ones we thought we understood. Every time scientists think they've figured out how the universe works, the cosmos throws a curveball that leaves even the brightest minds scrambling for answers. From stars that shouldn't exist to black holes that break the laws of physics, space is full of mysteries that defy logic. Today, we're diving into 20 of the most baffling moments where the universe looked at our scientific laws and laughed. Buckle up, because what you're about to discover might just change how you see everything beyond our planet. Back in the 1970s, something strange happened to two of NASA's most famous spacecraft, Pioneer 10 and Pioneer 11. These deep space probes were cruising through the solar system when scientists noticed they were slowing down in a way that shouldn't have been possible. According to Newton's laws of motion, their speed should have remained constant, but some unseen force was tugging them backward. For decades, this tiny but undeniable deceleration puzzled researchers, earning the name the Pioneer Anomaly. Was it a glitch, a flaw in the instruments, or something far more intriguing? At first, scientists suspected something as simple as heat radiating unevenly from the probe's power systems might be nudging them off course. But even after accounting for that, the anomaly persisted. Some theorists even proposed it could be a sign of undiscovered physics, a crack in the foundation of gravity itself. While later studies leaned toward thermal effects as the likely culprit, the mystery left a lasting question mark in the history of space exploration. What if there's more to gravity than we think? The pioneers may be silent now, but their unexpected journey still whispers secrets about the universe we don't fully understand. If you thought gravity was the ultimate force shaping the cosmos, think again. In the late 1990s, astronomers made a discovery that flipped our understanding of the universe upside down. Distant supernova, exploding stars used as cosmic measuring sticks, revealed something shocking. Instead of slowing down as expected, the expansion of the universe was speeding up. It was as if some invisible hand kept pressing the accelerator pedal on reality itself. Gravity, the force that should be pulling everything together, was losing the battle to something far stranger: dark energy. This mysterious force makes up nearly 70% of the universe's total energy, yet we still don't know what it truly is. Einstein once proposed a similar idea, the cosmological constant, but even he dismissed it as his greatest blunder. Now it's back with a vengeance, pushing galaxies apart faster and faster. Some theories suggest dark energy could be the energy of empty space itself, bubbling up from the quantum vacuum. Others speculate it might be an entirely new force of nature, one we haven't even named yet. The real kicker: if dark energy keeps accelerating the universe's expansion, the cosmos could end in a big rip, tearing even atoms apart. Or maybe we've got it all wrong, and a deeper law of physics is at play. Either way, dark energy stands as one of science's most humbling mysteries, proof that the universe still holds cards it hasn't shown us. And as far as cosmic rule breakers go, this one rewrites the book entirely. Galaxies should fly apart. That's the startling conclusion scientists reached when they first measured how stars move on the outer edges of spiral galaxies like our Milky Way. According to Kepler's laws of planetary motion, the same rules that govern Earth's orbit around the Sun, stars farther from a galaxy's center should move slower, their speeds dropping off predictably with distance. But when astronomers like Vera Rubin studied the rotation curves of galaxies in the 1970s, they found something bizarre. Those outer stars weren't slowing down. They were whipping around at nearly the same speed as stars closer in, as if some invisible anchor were holding them in place. The math didn't add up. Based on the amount of visible matter, stars, gas, and dust, those galaxies shouldn't have enough gravity to keep their outermost stars from flinging off into the void. Yet there they were, stubbornly defying expectations. The only explanation: Something unseen, something massive, must be warping space-time more than the visible universe could account for. Enter dark matter, the mysterious substance believed to make up roughly 85% of all matter in the cosmos. We still don't know what dark matter actually is. It doesn't emit, absorb, or reflect light, making it completely invisible to telescopes. Its presence is only betrayed by its gravitational grip on the galaxies we can see. Some theories suggest it's made of exotic particles that barely interact with normal matter. Others propose our understanding of gravity itself might need rewriting. Either way, this cosmic shadow remains one of the most profound puzzles in modern physics. And here's the kicker: without dark matter, galaxies as we know them wouldn't exist. Its gravitational scaffold is what likely allowed stars and planets to form in the first place. Yet after decades of searching, we've never directly detected it. Underground labs, particle colliders, and space telescopes keep hunting for clues, but dark matter continues to hide in plain sight, pulling the strings of the universe while staying just out of reach. For now, galactic rotation stands as both a triumph of observation and a humbling reminder. The cosmos operates by rules we're still learning to read. On a quiet August night in 1977, a radio telescope in Ohio picked up something that would become one of space's greatest unsolved riddles. The Big Ear Observatory, part of Ohio State University's search for extraterrestrial intelligence, SETI, was scanning the skies when a burst of radio waves erupted from the constellation Sagittarius. The signal was so strong, so perfectly aligned with what scientists expected an alien transmission might look like, that astronomer Jerry Amon circled it on the printout and scribbled one word in the margin: "Wow." This wasn't just noise. The signal blasted at a frequency of 1,420 MHz, a band where hydrogen, the universe's most common element, naturally emits energy. That made it a prime channel for any civilization trying to announce its presence. For 72 seconds, the WOW signal blared with 30 times the intensity of cosmic background noise before vanishing as suddenly as it appeared. Scientists raced to find a natural explanation. Could it have been a passing comet, a secret military transmission, a glitch in the equipment? Decades later, none of those theories hold up. The signal's narrow frequency range rules out most cosmic phenomena, and no human-made satellite was broadcasting at that exact spot at the time. Even more baffling, despite repeated searches, it's never been heard again. The WOW signal checks every box for what we'd expect from an intentional interstellar message except one: repeatability. If it was aliens, why wouldn't they transmit more than once? Unless we caught a fleeting moment when something or someone flickered on the cosmic radar before going silent forever. Whether it was a cosmic coincidence or a greeting lost in the void, one thing's certain: for those 72 seconds, the universe whispered something extraordinary. And we're still straining to hear the rest. Out of nowhere, in a fraction of a second, the universe flashes a signal so powerful it outshines entire galaxies. Fast radio bursts, or FRB, are among the most energetic and mysterious phenomena in space. These bursts last mere milliseconds, yet in that blink of cosmic time, they unleash as much energy as the sun does over days. First detected in 2007, these radio wave explosions arrive from deep space without warning, leaving astronomers scrambling to decode their origins. What could possibly produce such intense, fleeting signals? The leading suspect: highly magnetized neutron stars called magnetars. When these dense stellar corpses crack under unimaginable magnetic strain, they might release bursts powerful enough to match FRBs. Some even suggest colliding neutron stars or evaporating black holes could be the culprits. But here's the twist: a few FRBs repeat, flickering on and off in patterns that don't fit neatly into known astrophysics. Then there's the wildcard theory. Could these be signatures of advanced alien civilizations? While it's a long shot, the idea isn't entirely dismissed. A sufficiently advanced society might harness energy on a scale we can't fathom, perhaps unintentionally, or intentionally broadcasting their presence across the cosmos. The real challenge: FRBs are fast. By the time telescopes swing toward the source, the burst is already fading into silence. Yet with every new detection, we get closer to unraveling the puzzle. Some FRBs even come with a cosmic breadcrumb trail, a faint afterglow that hints at their birthplace in distant galaxies. One thing's certain: whether born from dying stars or something even stranger, fast radio bursts remind us that the universe thrives on extremes. And for now, they remain dazzling enigmas, brief cosmic fireworks that refuse to play by the rules. Black holes aren't just cosmic vacuum cleaners, they're also the universe's ultimate shredders. Or at least that's what physicists once thought. Here's the problem: when something crosses a black hole's event horizon, it's gone forever, right? Not so fast. According to quantum mechanics, information, the fundamental details of every particle, can never truly disappear. It might get scrambled, but it can't vanish. Yet black holes seem to break that rule, swallowing particles whole and leaving no trace of their original state. This clash between gravity and quantum theory is the infamous black hole information paradox, and it's been keeping scientists up at night for decades. Enter Stephen Hawking. In the 1970s, he proposed that black holes aren't completely black. They slowly leak energy, now called Hawking radiation, evaporating over eons until they vanish. But here's the catch: Hawking's math suggested this radiation was pure thermal noise, carrying zero information about what fell in. That meant when a black hole evaporated, all the data about swallowed stars, planets, or unlucky astronauts would be erased from existence. Quantum physicists recoiled. If true, the universe had a glaring bug in its code. The debate rages on. Some theorists argue the information does escape, encoded in subtle correlations within Hawking radiation, like a cosmic decoder ring hidden in the static. Others propose wilder fixes, like new particles called soft hair clinging to black holes, preserving data at their surfaces. Then there's the holographic principle, suggesting everything inside a black hole is secretly projected onto its event horizon, like a three-dimensional movie stored on a two-dimensional screen. But the boldest idea: maybe black holes don't vanish entirely. Instead, they could leave behind microscopic remnants, time capsules packed with compressed information, waiting for a future civilization clever enough to crack them open. Until we solve this paradox, one thing's clear: black holes aren't just bending space-time, they're bending the rules of reality itself. And tucked inside their darkness might be the key to unifying physics' greatest theories. The Big Bang should have left behind a cosmic fingerprint, an exact recipe of elements forged in the universe's first fiery moments, and for the most part it got the math right. Hydrogen, helium, their amounts match predictions perfectly. But there's one glaring exception: lithium. This lightweight metal, the same one powering your smartphone battery, is missing in action. According to nuclear physics models, the early universe should have cranked out 3 times more lithium than we actually observe. So where did it all go? This isn't just a tiny accounting error. The lithium problem strikes at the heart of our understanding of the Big Bang itself. Stars and supernova can't explain the shortage. They actually produce lithium over time, not destroy it. Some theorists suggest exotic physics might be to blame, like undiscovered particles altering nuclear reactions in the infant cosmos. Others propose lithium got burned up inside early stars in ways we don't yet understand. But the most tantalizing idea: maybe our measurements are wrong. Lithium is fragile. It breaks apart easily when exposed to heat, meaning the gas clouds we study today might have lost some of their original stash over billions of years. Or perhaps the universe had pockets of uneven temperatures during nucleosynthesis, skewing the element's production. Whatever the answer, this tiny discrepancy carries huge implications. If standard physics can't explain lithium's absence, we might need to rewrite part of the cosmic rulebook. It's a reminder that even our best theories are snapshots of a universe still full of surprises, one where something as simple as a missing element can upend what we thought we knew about creation itself. And here's the kicker: solving this puzzle could unlock secrets about the first minutes after the Big Bang, a time so remote that even light from that era faded eons ago. For now, the missing lithium stands as a quiet rebellion against our model's proof that the universe's opening act still holds mysteries we've barely begun to decode. The universe is supposed to be the same in every direction, no up, down, left, or right on the grandest scales. That's the cosmological principle, a cornerstone of modern astrophysics. But when scientists mapped the oldest light in existence, the cosmic microwave background, or CMB, they stumbled upon something deeply unsettling. The afterglow of the Big Bang isn't perfectly uniform. Instead, it shows a strange, unexpected alignment nicknamed the axis of evil. This isn't just a minor irregularity. The temperature fluctuations in the CMB appear subtly organized along a particular plane, almost as if the universe has a hidden, preferred direction, a cosmic North Star we didn't know existed. If confirmed, this could upend one of astronomy's most sacred assumptions, that the universe is isotropic, meaning it looks the same no matter where you're standing. Some argue it's just a statistical fluke, a trick of the data. After all, the signal is faint and noise creeps into even the most precise measurements. But others see a crack in the foundation. Could this be evidence of something deeper, a shadow of a multiverse brushing against ours, the imprint of an ancient space-time warp from before the Big Bang? Or worse, a sign that our models of cosmic inflation, the theory explaining the universe's smoothness, might need a radical revision. The name axis of evil was coined half-jokingly, but the implications are deadly serious. If the universe does have a preferred axis, it means our place in space isn't random. We'd be forced to reckon with the unnerving idea that our cosmic neighborhood is special, a direct challenge to Copernicus's insistence that Earth holds no privileged position. For now, the mystery lingers. New telescopes probe deeper into the CMB's whispers, searching for answers. Whether this axis is a cosmic illusion or a paradigm-shattering truth, one thing's certain: the universe keeps nudging us to question what we think we know. And sometimes the most unsettling discoveries are the ones that remind us we might just be scratching the surface. Astronomers have witnessed countless stars flicker, but none have baffled them quite like KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, this seemingly ordinary star does something extraordinary. It dims unpredictably, sometimes dropping in brightness by a staggering 22%. These aren't the gentle, rhythmic dips caused by orbiting planets. Instead, the star's light flickers in chaotic, asymmetrical patterns, as if something massive and utterly unnatural is passing in front of it. When the Kepler Space Telescope first spotted this odd behavior in 2015, scientists scrambled for explanations. Dust clouds, maybe, but the star's light dims unevenly across different wavelengths, a detail that doesn't quite fit. Swarms of comets, unlikely no known comet family could block that much light. Then came the wildcard theory. Could this be evidence of an alien megastructure, like a Dyson sphere under construction? The idea sent ripples through the scientific community, reigniting dreams of detecting intelligent life beyond Earth. But here's the catch: science thrives on repeatable evidence, and Tabby's star refuses to follow a script. Follow-up studies revealed the dimming isn't consistent. It varies over years, even decades. Some observations suggest fine space dust might still be the culprit, scattering starlight in strange ways. Yet the lingering question remains: why does this particular star behave like no other? The mystery goes beyond alien hunts. If natural, Tabby's star challenges our models of stellar evolution and planetary formation. If artificial, well, that rewrites the story entirely. Either way, this cosmic oddity reminds us that the universe has a flair for drama, hiding its most perplexing secrets in plain sight. And while the megastructure theory remains a long shot, the star's stubborn refusal to be explained keeps the door wide open to possibilities we've barely begun to imagine. One thing's certain, Tabby's star is more than a curiosity. It's a beacon illuminating just how much we still don't understand and how thrilling the hunt for answers can be. Physics textbooks have one rule written in stone: for every action there's an equal and opposite reaction. That's Newton's third law, the foundation of rocket science. Yet in the early 2000s, an engineer named Roger Shawyer claimed to have built an engine that defied it. The M drive, short for electromagnetic drive, wasn't supposed to work. No fuel, no exhaust, just a metal chamber bouncing microwaves around, and somehow it seemed to generate thrust. The numbers were tiny, just a few millinewtons, barely enough to nudge a sheet of paper. But if real, those whispers of thrust could rewrite space travel. Imagine spacecraft accelerating indefinitely without fuel, reaching Mars in weeks instead of months. NASA Eagleworks lab took notice, running their own tests in 2016. The results inconclusive but tantalizing. Their M-drive prototype produced a faint push even in a vacuum. Cue headlines proclaiming the death of physics as we knew it. Skeptics weren't convinced. Some argued the thrust was just experimental error, heat warping the device, or magnetic interference. Others pointed out the M-drive appeared to violate conservation of momentum, a bedrock principle of physics. If momentum isn't conserved, the universe as we model it falls apart. Then came the twist. Independent labs, including one in Germany, found subtle thermal effects that might explain the anomaly. The microwaves could be heating the air inside the chamber unevenly, creating tiny currents that mimicked thrust. Case closed, not quite. Some researchers insist there's still an unexplained residue of force, something beyond known physics. The debate rages because the stakes are cosmic. If the M-drive does work, it hints at undiscovered interactions between quantum fluctuations and spacetime, a loophole in Newton's laws. If it doesn't, it's a cautionary tale about how easily hope can masquerade as science. For now, the M-drive sits in a gray zone, too bizarre to accept, too intriguing to ignore. It's a reminder that even our deepest scientific convictions are provisional, waiting for the next experiment, the next outlier, the next crack in the cosmic rulebook. And whether it's a revolutionary thruster or a brilliant mirage, it proves one thing: the universe loves keeping us guessing. The moon hangs in our sky as a silent, cratered companion, seemingly frozen in time. But hidden within its ancient rocks lies evidence of a turbulent past that defies expectations. When Apollo astronauts brought back lunar samples, scientists made a startling discovery: some of these rocks were magnetized. That shouldn't be possible. Today's moon is geologically dead, with no global magnetic field to speak of. Yet billions of years ago, something gave it a magnetic shield rivaling Earth. How could a world so small generate such power? Dynamo theory. The same process that fuels Earth's magnetic field requires a churning, molten core. But the moon's modest size means its core should have cooled and solidified eons ago. So what kicked off this lunar powerhouse? One bold idea suggests the moon's core stayed molten far longer than models predict, possibly heated by radioactive elements or tidal forces from a younger, closer Earth. Another theory points to massive asteroid impacts, which might have stirred the moon's interior like a cosmic blender, jump-starting a temporary dynamo. Then there's the wild card: external magnetization. Could the moon have borrowed a magnetic field from Earth during their early, intimate dance? Some simulations show our planet's magnetic influence might have stretched far enough to imprint on the moon's surface rocks, a celestial handshake frozen in stone. But the plot thickens. Recent studies reveal the moon's field didn't just flicker briefly, it persisted for over 1 billion years. that longevity deepens the mystery. If impacts or Earth's influence were the cause, why did the field last so long? The answer might lie in the Moon's early mantle, which could have acted like a thermal blanket, trapping heat and keeping the core simmering against the odds. Every new lunar mission peels back another layer of this enigma. Whether it's a story of forgotten inner fire, cosmic collisions, or planetary teamwork, one thing's clear. The Moon's magnetic past is a reminder that even the quietest worlds can harbor explosive secrets. And as we prepare to return to its surface, we're not just exploring a barren rock, we're decoding a relic of a time when the Moon was anything but still. Cosmic distances aren't just vast, they're also surprisingly slippery to measure. For decades, astronomers have relied on two reliable methods to calculate how fast the universe is expanding, a number known as the Hubble constant. The first approach studies nearby objects like Cepheid variable stars, whose predictable brightness allows precise distance measurements. The second method analyzes the cosmic microwave background, the afterglow of the Big Bang, filled with subtle clues about the universe's infancy. Both techniques should point to the same expansion rate, but they don't. In fact, the gap between them keeps widening, a stubborn mismatch now called the Hubble tension. Here's the problem. Local measurements suggest the universe is expanding about 73 kilometers per second per megaparsec. Meanwhile, observations of the ancient cosmos peg it around 67. That 6-kilometer difference might seem minor, but statistically, it's like two watches disagreeing by hours every day. Either we're missing something in our observations, or the universe played a trick on us. Some scientists suspect hidden errors. Maybe Cepheids aren't as uniform as we thought, or dust interferes with their light. Others argue the discrepancy might reveal cracks in our cosmic model. Could dark energy's strength have changed over time? Is there an unknown particle influencing expansion? The wildest theories suggest our universe collided with another bubble of spacetime early on, leaving behind wrinkles in the Hubble constant. Each new study deepens the mystery. In 2023, the James Webb Space Telescope confirmed earlier measurements, ruling out some instrumental errors. Meanwhile, independent techniques like tracking gravitational waves from neutron star collisions have started weighing in, adding fresh data to the debate. At its core, the Hubble tension isn't just about numbers. It's a cosmic tug of war between how we think the universe works and what it's actually doing. Whether this leads to revised instruments or revolutionary physics, one thing's certain: the cosmos refuses to make it easy. And that's what makes this puzzle so thrilling, because every contradiction is an invitation to dig deeper, to question further, and maybe, just maybe, to rewrite the rules. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing countless stars and planets. Given those numbers, the math screams a simple conclusion: we shouldn't be alone. Statistically, intelligent life should have emerged elsewhere, perhaps even thrived. So where is everyone? This is the Fermi paradox, a puzzle that gnaws at the heart of astrobiology and leaves scientists grappling with a haunting silence. Enrico Fermi, the legendary physicist, first posed the question in the 1950s during a casual lunchtime conversation. If alien civilizations were common, he reasoned, they should have colonized the galaxy by now, or at least left some trace we could detect. Yet decades of searching have turned up empty. No signals, no megastructures, no interstellar visitors, just radio static and cosmic quiet. One chilling explanation is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar scales. Maybe the filter lies in our past, like the near-impossible jump from single-celled organisms to complex life. If so, we're the lucky outliers who slipped through. Or worse, it could still be ahead of us. Climate collapse, nuclear war, runaway AI, any of these could be the universe's way of culling civilizations before they spread too far. Then there's the zoo hypothesis, the idea that advanced civilizations are deliberately avoiding us, treating Earth like a nature preserve. It's a comforting thought until you realize it implies we're being observed like animals in a cosmic safari park. Other theories suggest we're simply too early or too late that intelligent life blooms in waves across the universe, and we're either among the first or destined to arrive after the party's over. But the most unsettling possibility that we're fundamentally wrong about how life emerges. What if intelligence like ours is freakishly rare, or the universe is far more hostile to complex life than we've assumed? The silence might not be a mystery, it could be the answer. The Fermi paradox forces us to confront our place in the cosmos. Are we a fluke, a cautionary tale, or just one voice in a chorus we haven't learned to hear yet? Until we know, the stars remain eerily quiet and the question lingers unanswered in the dark. In October 2017, astronomers spotted something streaking through our solar system that looked like nothing we'd ever seen before. Long, thin, and tumbling end over end, the object named Oumuamua, Hawaiian for scout, was the first confirmed visitor from another star system, but its strangeness didn't stop at its shape. As it hurtled away from the sun, something defied all expectations. It sped up. Gravity alone couldn't explain this sudden acceleration. Comets often get a boost from outgassing sunlight, vaporizing their ice, creating jets that act like natural thrusters. But Oumuamua showed no visible coma or tail, the usual hallmarks of outgassing. If it wasn't gas, what was pushing it? One theory suggests hydrogen ice, an exotic type of frozen gas that could vaporize invisibly, nudging the object without leaving a trace. Another idea proposes it was a cosmic dust bunny, a fragile aggregate of interstellar material so lightweight that even sunlight could have given it an extra kick. Then came the more provocative hypothesis: could Oumuamua have been artificial? Harvard astrophysicist Avi Loeb famously raised the possibility it might be a light sail, a thin, propelled structure designed for interstellar travel. While most scientists lean toward natural explanations, the mere debate forced astronomers to confront how little we know about objects from beyond our solar system. Oumuamua's legacy isn't just about one mystery. It exposed gaps in our understanding of how interstellar visitors behave, how they move, what they're made of, and how often they pass through. Since then, telescopes have been scanning the skies more intently, leading to the discovery of additional interstellar objects like the comet Borisov. Each new visitor offers clues, but none have matched Oumuamua's enigma. Whether it was a peculiar fragment of an alien planetary system or something even more extraordinary, Oumuamua left us with a humbling lesson. The universe is full of objects that don't fit our textbooks, and sometimes the strangest ones are the ones that teach us the most. Imagine two coins flipped on opposite sides of the universe. No matter how far apart, they always land on the same side. That's the bizarre reality of quantum entanglement, a phenomenon so strange even Einstein called it spooky action at a distance. Here's how it works. When two particles become entangled, their properties like spin or polarization link together mysteriously. Measure one, and its partner instantly snaps into a corresponding state, regardless of the miles or light years between them. This isn't just theoretical. Labs have confirmed it repeatedly, firing entangled photons through fiber optics or even into space, where they still coordinate faster than light could travel between them. By classical physics, this should be impossible. Einstein's relativity sets light speed as the universe's ultimate speed limit, yet entangled particles flout this rule effortlessly. So what's really happening? The catch is, no information actually travels between them. You can't use entanglement to send a message. The correlation only reveals itself when you compare measurements later. Think of it like opening a pair of magical envelopes, one on Earth, one on Mars. Each contains a random word until you open one, which instantly determines the other. But until you check, neither word exists in a fixed state. Quantum mechanics explains this through superposition. Particles exist in multiple states at once until observed, and entanglement extends that fragile uncertainty across space. Some interpretations suggest entangled particles aren't separate entities at all, but facets of a single quantum system, stretching the definition of object to cosmic scales. Others propose hidden variables we haven't discovered yet. Whatever the answer, entanglement isn't just a lab curiosity. It's the backbone of emerging tech like quantum computing and cryptography, where particles perform synchronized dances no classical system could replicate. And as experiments push entanglement to ever greater distances, one thing becomes clear. The universe has a hidden layer of connection, one that laughs at our everyday notions of space and time. For now, this spookiness remains one of nature's deepest puzzles. But every time we untangle a piece of it, we're not just breaking rules, we're rewriting them. Somewhere in the depths of space, an invisible titan is bending the rules, pulling thousands of galaxies, including our own Milky Way, toward a point we can't even see. Scientists call it the Great Attractor, a colossal gravitational anomaly lurking about 250 million light-years away in the direction of the constellation Centaurus. This thing shouldn't exist, at least not with this much power. Here's what makes it so strange. According to our maps of cosmic expansion, galaxies should be drifting apart, carried by the flow of dark energy. Instead, something unseen is dragging entire clusters of them toward a single spot in space, like a cosmic whirlpool hidden behind a curtain. And that curtain has a name: the zone of avoidance. This region of the sky is shrouded by the dense dust and stars of our own galaxy's plane, blocking our view of what lies beyond. For decades, astronomers could only guess at the Great Attractor's true nature. Some speculated it might be a supercluster of galaxies so massive it warps spacetime on a staggering scale. Others wondered if it was the footprint of something even bigger, a structure beyond our current understanding of cosmic architecture. Then, in the 21st century, telescopes piercing through the galactic haze revealed a clue: the Norma cluster, a dense knot of galaxies with enough gravity to account for some, but not all of the pull. So what's doing the rest? One theory points to an even larger structure, the Shapley supercluster, lying beyond the Great Attractor like a hidden puppeteer. But even that might not explain the full force at work. Could there be exotic matter or unknown physics amplifying gravity in this region? Or is the Great Attractor just one piece of a vast, interconnected web of dark matter filaments, tugging the universe into motions we're only beginning to trace? Every new survey peels back more of the mystery. Infrared and radio telescopes now map the zone of avoidance in unprecedented detail, revealing galaxies previously hidden behind the Milky Way's glare. Each discovery sharpens the picture, but the Great Attractor remains elusive, a reminder that even as we chart the cosmos, some forces refuse to stay within the lines. And perhaps that's the most thrilling part. The universe isn't just expanding, it's being pulled, sculpted, and rewritten by giants we're still learning to see. Science thrives on the thrill of discovery, but sometimes what looks like a revolution turns out to be a loose cable. In 2011, physicists at the Opera experiment in Italy recorded something impossible. Neutrinos, those ghostly particles that barely interact with matter, seemed to be breaking the universe's speed limit. Their measurements suggested these tiny messengers were arriving 60 nanoseconds faster than light could travel the same distance. If true, Einstein's theory of relativity, the foundation of modern physics, was in trouble. Headlines exploded. Had we finally found a crack in relativity's ironclad rules? The implications were staggering. Faster than light travel could rewrite causality, turning science fiction into reality. But the physics community reacted with healthy skepticism. Extraordinary claims require extraordinary proof, and this one had a problem. Months of frantic cross-checking revealed the culprit: a faulty fiber optic cable connecting a GPS receiver to a computer. The lag it introduced had skewed the timing just enough to create the illusion of superluminal speed. Once fixed, the neutrinos fell back in line with Einstein's predictions. Case closed mostly, yet this episode wasn't just about a technical glitch. It highlighted how carefully scientists walk the line between hope and rigor. One loose connection nearly upended physics, but the system worked. Peer review, replication, and relentless scrutiny caught the error before it misled us. That's how science self-corrects, by doubting first, celebrating later. But here's the fascinating part: mistakes like this actually strengthen our search for truth. They remind us to question even the most solid-seeming results, and sometimes, buried in the noise of false alarms, real anomalies emerge. Neutrinos still hold mysteries: why they have mass, how they oscillate between types, and future experiments might yet reveal physics beyond our current understanding. So while the faster-than-light neutrinos were a false alarm, they taught us something vital. Every oops moment is a masterclass in humility, and proof that in science the most thrilling discoveries often start with the courage to say, "Wait, that can't be right." Because sometimes it isn't, and sometimes, against all odds, it is. Some corners of the cosmos feel crowded, galaxies packed tight like commuters on a rush-hour train. Then there's the Boötes void, a yawning chasm so empty it defies logic. Stretching 330 million light-years across, this vast desert of space contains only a handful of galaxies where thousands should thrive. If you dropped the Milky Way in here, our nearest galactic neighbor would be almost unimaginably distant. At first glance, the void seems like a statistical hiccup, like rolling a die 1,000 times and landing on 6 just once. But the scale of this emptiness is far stranger than mere chance. Most large voids in the universe are sponge-like, woven with filaments of galaxies. The Boötes void, it's more like a cosmic clean room scrubbed nearly bare. So what could carve out such a perfect vacuum? One radical idea points to cosmic strings, hypothetical defects in spacetime left over from the Big Bang. Think of them as cracks in the universe's foundation, so dense they warp everything around them. If one sliced through this region long ago, it might have pushed matter aside like a plow through snow, leaving behind this eerie emptiness. Others suggest the void isn't truly empty, just hiding something. Dark energy's repulsive force could be accelerating galaxies away faster here, creating the illusion of a ghost town. Or perhaps an ancient collision between universes in the multiverse left behind this scar. But here's the twist: the few galaxies that do call the void home are oddly isolated, glowing like lone streetlights in an endless night. Their very existence challenges theories about how galaxies form in undercrowded environments. Each one is a cosmic rebel, surviving where nothing should. The Boötes void doesn't just baffle astronomers, it invites us to rethink what normal even means in the universe. Whether it's a fluke or a fingerprint of something deeper, one thing's certain: sometimes the most profound mysteries aren't about what's out there but what isn't. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, then white holes are their bizarre, rule-breaking opposites: cosmic fire hoses blasting matter and energy outward with relentless force. These theoretical rebels exist as solutions to Einstein's equations, acting like black holes in reverse. While a black hole's event horizon is a point of no return, a white hole's horizon is a point of no entry. Nothing gets in, but everything gets ejected. The idea alone flips cosmic logic on its head. White holes defy the second law of thermodynamics, which states that entropy, or disorder, always increases over time. Instead of swallowing light and matter, these hypothetical objects would spew them out in a chaotic fountain, effectively decreasing entropy in their surroundings. That's like watching a shattered vase reassemble itself mid-air. Physics simply doesn't allow it under normal circumstances. So why do mathematicians take white holes seriously? General relativity treats time as symmetrical, meaning the equations describing a black hole's collapse could, in theory, run backward to describe a white hole's explosion. Some researchers speculate white holes could be the other end of black holes, connected via wormholes in a dizzying cosmic loop. Others propose they're ancient black holes from a previous universe, erupting into ours like seeds from a dying cosmos. Yet here's the catch: no one's ever spotted one. If white holes exist, they'd be phenomenally unstable, likely collapsing into black holes the instant they formed. Their very nature makes them fleeting, more like cosmic hiccups than permanent fixtures. Still, the search continues. Some astronomers have scoured gamma-ray bursts and unusual radio signals for hints of white hole activity, but so far the universe hasn't handed us proof. Perhaps the most thrilling aspect of white holes isn't whether they're real, but what their possibility reveals about our models of reality. They remind us that physics is a dialogue, not a monologue, a set of ideas constantly tested against the universe's creativity. And if one thing's certain, it's that space-time still has surprises tucked up its sleeve, waiting for the right moment to defy expectations once again. Tucked away in the constellation Eridanus lies a cosmic cold spot so baffling it makes astronomers question everything they know about the early universe. When scientists first mapped the cosmic microwave background, the afterglow of the Big Bang, they expected a mostly uniform glow, dotted with tiny temperature variations. But this region, it's too cold, dipping far below what standard inflation theory predicts. Stretching over 1 billion light-years, this anomaly, dubbed the Eridanus supervoid, shouldn't exist. Yet there it is, a cosmic bruise that refuses to fade. One explanation points to a void, a vast, underdense region of space where galaxies are unusually scarce. If such a void existed, light passing through it would lose energy as it climbs out of the void's gravitational well, creating a cold imprint in the CMB. The problem: a void this big would require an almost impossible alignment of chance, like rolling 100 dice and landing all ones. Even then, simulations suggest it wouldn't fully account for the temperature drop. That's where things get wild. Some theorists propose this cold spot could be evidence of a cosmic defect, a relic of exotic physics from the universe's first moments. Think of it as a scar left behind by a phase transition in spacetime itself, like cracks in ice as it freezes. Others dare to suggest it might be a fingerprint of something even bigger, a collision with another universe in the multiverse. If true, this spot could be the first tangible clue that our cosmos isn't alone. Yet skeptics push back. Could instrumental noise or foreground dust be skewing the data? New telescopes like the Atacama Cosmology Telescope have scrutinized the region, confirming the cold spot's existence but leaving its cause wide open. The debate isn't just academic, it cuts to the heart of how we understand cosmic inflation and the large-scale structure of reality. Whether it's a statistical fluke, a hidden void, or a portal to another universe, the Eridanus supervoid remains one of cosmology's most tantalizing puzzles. And until we crack it, this icy enigma serves as a humbling reminder. Even the oldest light in the sky still has secrets to spill. After journeying through these 20 cosmic enigmas, one truth becomes undeniable. The universe operates on a scale of mystery we've only begun to measure. Every time we think we've decoded its rules, space throws us a curveball, reminding us that the cosmos thrives on the unexpected. From black holes shredding the fabric of reality to invisible forces tugging galaxies off course, these anomalies aren't just quirks, they're invitations to dig deeper. Science doesn't advance by confirming what we already know. It grows when confronted with the inexplicable, the outliers that refuse to fit. These 20 mysteries represent more than gaps in our knowledge, they're the frontiers where discovery happens. Whether it's dark energy's relentless push or the eerie silence of the Fermi paradox, each one challenges us to rethink, re-examine, and sometimes rewrite the textbooks. So which of these cosmic rebels fascinates you the most? The star that dims like no other, the phantom tug of the great attractor, or perhaps the whispers of an alien signal lost to time? Drop your thoughts in the comments. We're all part of this grand conversation, unraveling the universe's secrets together. And if you're hungry for more mind-bending mysteries, don't forget to subscribe. The cosmos isn't done surprising us yet, and neither are we. The next breakthrough, the next rule shattered, it's all out there waiting. After all, the greatest thrill isn't just finding answers. It's realizing how many questions we've yet to ask.